All right, so this is part 2, if you will, of the Cartesian coordinate system that we started yesterday. And we're going to start very much where we ended last time with talking about x and y intercepts of lines. We're just looking at lines that are a little bit maybe more complexly written, and then we'll move into some other things. So we're going to start by finding the x and y intercepts of these lines, and then specifically using those to graph our graph, our equation. So to start with, when we find x and y intercepts, what we do is we let the x values and the y values respectively equal 0, and we solve. So when I'm finding the x-intercept, then I'm actually letting y equal 0. So if I let y equal 0 here, what will I get for x? 2. X is going to be 2, either written out longhand or looked at so that you can just see visibly what this one would be. So this would be the x value of 2, the y value of 0, and I can plot that. Would be right here. And then to find my y-intercept, I let x equal 0. That's a mess. So this would be 2 times 0 minus y equals 4. Okay, so what would y have to equal in order to make that equation true? Yeah, y would need to be negative 4. And again, if you need to see more work to see that, then continue working through the problem in full to do so. So this would be x is 0 and y is negative 4. So these are my x and my y intercepts. So 0, negative 4 would be here. And then I'm going to connect these two with a line. I mentioned it when I recorded the video the other day. Really, you should have arrows on the end of your line. Otherwise, it doesn't really mean that it's a line. So we'll be precise and go and put those on there. Okay, so feels like what we did yesterday, right? Kind of a compilation, maybe a little bit of a couple things, but very much the same. The next graph I need to draw for you before we can get started with it, okay? So the directions are to use this graph that I need to draw for you first. So just hold tight while I draw the graph, okay? And then we're going to actually find the intercepts of the graph. So let me get them plot everything on there first. Okay, so this is my graph. You'll start with a graph given to you already too. This is not a line, right? It's not. And maybe you recognize what this is a graph of. I don't know. Does anybody happen to recognize what this is a graph of? Do you remember it? It's an absolute value graph. And we're going to see it here in a minute too when we are actually graphing some of these. But what I wanted to show you about this is that sometimes you have more than one x-intercept. We only have one y-intercept when we're working, but we sometimes have more than one x-intercept. So when we're looking at this graph, we're going to find our x-intercepts, and there are 2 of them, and our y-intercept, and there's always at most one of those. So what do you see as values for x-intercepts here? Okay, so right here, there's a negative 4, 0. So negative 4, 0, and then what's the other one you saw? 0, 0, right? Okay, so there's my other x-intercept. Negative 4, 0, and 0, 0. Okay, written as ordered pairs. Now then, what about y-intercept? Yeah, it happens to share one, right? It's also going to be 0, 0 for this one, the y-intercept is. Okay, so we've said x-intercept let y equals 0, y-intercept let x equals 0. And when we're working with lines, as McKaylee pointed out to us early on, sometimes we can eyeball it pretty quickly. We don't really have to write down a whole lot to solve them, right? That happens. But when equations are not lines, it becomes more tricky to do that. So here's an example of one, number 3, and then number 4. These are not lines. The first one is a quadratic or a polynomial. You can use either of those words for it. The second one's a rational. So I want to show you that the process still works, it's just more work to find our values. So we're going to find x and y intercepts, and alphabetically speaking, we'll find x-intercept first. So the x-intercept is when y equals 0. So this would be 0 squared plus x minus 16 equals 0. What would x have to be to make that statement true? Positive 16 is right. Right? So if you sort of ignore this piece, and x were 16, then 16 minus 16 is 0. Is everybody good with that? So my x-intercept is 16, 0. The y-intercept is the one that's actually harder to do on this one. My y-intercept, which is when x equals 0, means that I have to go like this. I have to do y squared. Oh, I know what I said wrong before, but I'll fix it in a minute. Plus the 0 for the x, and then minus 16 equals 0. So I need a y value that makes this statement true. And it's kind of tricky written this way, but it'll be easier if, actually let me do this. If I move my 16. So if I've got y squared equals 16, what values for y make this statement true? 4. What else? And negative 4. Right? We've solved equations like this already in this class. We did it with square roots. Do y'all remember that? And we talked about the fact that when we take square roots, we put plus or minus on them. And the reason is because 4 times 4 is 16. But negative 4 times negative 4 is also 16. So there are 2 values here that I get, positive and negative 4. So if I write these out, I have 0, 4, and I have 0, negative 4. My pause earlier was because I made the mention to you that we have at most one y-intercept, and this one has 2. The reason is because this one is actually something that's called not a function, and I didn't remember that we had an example of that in your notes. We don't have an example of a graph of one of those. So I'll take myself back and say that sometimes you'll have more than one y-intercept if you're working with the equations in this lesson as well. I'd forgotten we had that in here. So we have 2 y-intercepts on this one. How about number 4? Okay, so we'll find our x-intercepts. X-intercept is the easy one to do on this one, always. For an equation like this. I said it backwards. The y-intercept's the easy one to do. The x-intercept's the hard one to do on these. So here's 0. 1 minus x squared over 5 plus x squared. Now, if you can eyeball that example as an answer, you're doing really good. Because I have a difficult time looking at that one, deciding what my answer is from the just, spur of the moment look. One of the things that's kind of cool that you'll like really quickly is that the denominator goes away because I can cross multiply. Right? So when I cross multiply that denominator times 0, what happens? It's 0, right? So when I multiply here, I get 0 equals 1 minus x squared. And that always happens when we're dealing with rational equations set equal to 0. Okay, so if we've got 0 or y equals and we've got y equals 0, then that's always going to happen. The denominator ends up going away. Now the numerator, 1 minus x squared, is actually set equal to 0 at this point. Let's move the x squared to the other side, and then it looks a lot like the last problem. I have x squared equals 1. So what value or values can x equal? Yeah, positive 1 and negative 1. So I have on this one 2 x-intercepts. I have 1, 0, and I have negative 1, 0. All right, the y-intercepts on an equation like this are the ones that are very nice for letting x equal to 0. So if I have the y-intercept here, I've got y equals 1 minus 0 squared over 5 plus 0 squared, which is what? Got lots of zeros, so what do I have? 1 over 5. Yeah, exactly. It's just the constant parts. So I have x is 0, y is 1 over 5. Not necessarily something I would love to graph, right? But it's easy to find. All right, so what we're going to do next, now that we've sort of encountered finding the x and the y intercept component for equations that aren't lines, is we're going to graph some equations that aren't lines. And Alexandra is right when she asked the question earlier, like there seems like there's so much flexibility, and there is a lot of flexibility, but I'm going to make it a little bit easier by giving some basic guidelines on this particular one. Now, when we were working with lines, we only needed to plot 2 points, right? Because every 2 points determines a line. That was very straightforward. When we're working with other graphs, it's not enough to plot 2 points. So when a graph is not a line, it requires more points to plot it. We want to try to choose well with at least 5 points, and the numbers -2, -1, 0, 1, and 2 are often good choices. Are they the only choices? No, they're definitely not. And if you see another option that you like better, go for it. But these are often going to be good choices for the types of equations we're dealing with on this assignment, okay? So we're going to create a table, an XY chart, and we're going to have at least 5 values on it. All right, does everybody have that one down? Are we good? Okay. So here's our first equation. And on this one, you see absolute value symbols. Do you remember those? We haven't specifically talked about absolute values in this class, I don't think. Have we? I don't feel like we have. But absolute values take whatever value is inside of it, and it becomes positive. It's a distance is what it really is. So if you're at -2, the distance back to 0 is 2. If you're at +2, the distance back to 0 is 2. So this is our equation. I've got 3 times the absolute value of x, and I'm going to create an XY chart, and I'm going to choose those same numbers that I mentioned on the previous slide, -2, -1, 0, 1, and 2. How much work you show on this really depends on how comfortable you are with the type of equation you're dealing with, all right? So if you're really comfortable with absolute values, you're probably going to be able to do this in your head. If you're less comfortable with it, you might want to jot down a few things as you work to make sure that you don't make a mistake. And absolute values are not the only functions we're about to deal with. There's a couple of others we're going to deal with too. So as we are taking a look at this, the positive ones are the easiest ones. So let's actually start with 0 and go down. If I put in 0, what is the absolute value of 0? It's 0, and 3 times 0 is 0, right? So that one's the most straightforward. Over here, what if I put in 1? You get 3, right? Absolute values don't change positives, so this is 3. What if I put in 2? 6. Okay, so the positive ones are the easy ones because they don't change. If you put in negatives, so let's actually do the -2 now. So if I have 3 and I have absolute value -2, what is the absolute value of -2? 2, and then 3 times 2 would be 6. What if we put in -1? It'll just be a regular 1, and then times 3 would be 3. Okay, so we've got 5 points that we plot now. So I would like for you to plot your 5 points. I'll plot the 5 points on the screen as well. And then I'm going to show you how to connect it. So don't connect anything until we've all plotted our points. Any guess as to what shape you think this is creating? Good guess. It's not a U. It's a V. Absolute values have V's. So if you want to think value V, that works, right? Absolute value graphs will look like V's. What they really look like is they look like two lines or two half lines that meet at the bottom of the V. They're straight. Absolute values have two components that are straight lines. Okay? So anytime you see an absolute value graph, you're going to have a shape of a V. Yes, ma'am?
Arrows on this one?
Yep, we do. I didn't get mine on there yet. Good catch. They still go up on the ends, you betcha. Okay, so let's try another one. Different graph. Not a V. All right, this is a graph of a parabola. We'll learn and talk more about those when we get into college algebra. But for what we're doing right now, we're creating ordered pairs and plotting them. Again, the same ordered pairs I chose before work out very nicely. And I'm going to do the positive ones first because they're the more straightforward, easy ones to do. What happens if I put it, well, I'll start with 0. What happens if I put in 0? I get 0, right? 0, we would square first. 0 squared would be 0, and then the opposite of 0 is still 0. Let's put in 1. Remember, order of operations, we square first. So what's 1 squared? 1. And then I have a negative in front of it, so it gives me a negative 1. And my 2. 2 squared is 4. And then I put a negative in front of it, so I get negative 4. Okay? Positive ones are the easiest. Let's actually write the negative ones down, or at least I will. I have negative of negative 2 squared. I square first. Order of operations. What is negative 2 squared? It's 4 with a negative that's still in front of it, so the result is still a negative 4. And if I put in a negative 1, what is negative 1 squared? 1 with a negative in front of it gives me a negative 1. So let's plot those points now. I told you it's not a V. So what do you think it is? It looks like a U. Yeah, it looks like something akin to a U. There is curvature to it that's not straight. It's not straight and rigid, it is curved, okay? So when you're connecting this, it will look something like this. And anytime you have x squared, you're going to have a U shape. There's one more shape we're going to talk about, though. Oh, I've got another example of a quadratic first before I do that. Okay, is everybody good with this one? Okay, how is this one different than the last one? There's another number on it, right? I have a +5 at the end. Okay, so I can still use the same xy's that I did before. All that stuff is the same, so don't let that throw you. Let's just see how it ends up looking different. So I have negative 2, negative 1, 0, 1, and 2. And we'll start with the positive part and go down because I kind of like those numbers better. 0. What if I plug 0 in? What am I going to get? I'm going to get 0 at the beginning and then 5 when I add the 5 at the end, right? So I'm going to get 5, right? What about when I plug 1 in? Okay, so these are harder to see in your head because you got the extra 5 on the end. So if you need to write some stuff down, please do so. If I plug in the number 1, I'll just do my scratch work at the bottom. I have 1 squared, which is 1, and then the negative in front of it makes it a negative 1, plus the 5 at the end makes it a 4. How about if I do a 2? I'll get just a 1, right? So I'll get negative, so 2 squared is 4. With the negative in front makes negative 4. and then plus the 5 at the end. So negative 4 plus 5 is 1. And you're welcome to grab a calculator to put these in and do them more quickly. You don't have to think through every single one of them in your head, okay? So yeah, this is 1. All right, let's go back up now and get negative 2 and negative 1. So I've got, oops, negative 1 squared, or negative 2 squared. So what's negative 2 squared? 4 with a negative in front makes negative 4, plus the 5 at the end makes 1. And how about negative 1 squared? It makes 4. Do you see any pattern kind of things happening in my y values in all 3 problems that we've done so far? They're like mirrored, and we're going to talk about that in just a minute. Okay, so let's actually plot these first. Negative 2, 1. Negative 1, 4. 0, 5. And reversed. Okay, so still look like a U. Graphically, compare this graph to the one you just did. How are they different? Nope, but that's a good guess. It's not thickness. It moved up 5. It's like you take the whole thing and you just shifted it up 5. But look at the equations. Do you see why that should make sense? Yeah, these equations are identical, except that I added 5. In fact, when I flip back and forth between my screens, you can even see it moving, can't you? Look at that. Ah, that's cool. I didn't expect to do that for you, but that was fun. Nice. Fun technology. So I couldn't do that on chalkboard, right? It's totally technology for you. All right. Are you guys ready for another one? Different graph. Okay, so we did absolute values. We've done x squareds. And the last one that we're going to do as a type of graph in this unit is x cubed. Okay? Same set of points that we're going to use. This isn't the super friendliest, but it's not terrible. So I'm going to stick with my same points because they work. Okay, what happens when I put in 0? Y'all know. 0. It's 0. Okay, good. Right? 0 cubed and 0, and we got lots of zeros going on. Okay. How about 1? What is 1 cubed? It's 1, and then times the 3/4 would give me 3/4. So that's why I say this is not the super friendliest, because I do have a fraction involved. But the rest of them are kind of nice. So let's take a look at what happens when I plug in 2. What is, remember, we don't multiply first, right? We cube first, powers first. What is 2 cubed? 8. So what is 3/4 times 8? It's 6. This 4 reduces with the 8 to give me a 2, and 3 times 2 is 6. Okay, very good. Now let's go back up and get the negative 2. What happens when I have negative 2 instead of positive 2 in this one? It's actually negative 8 this time, right? Because there's 3 of them. That's different than when we did squares. Squares eliminate negatives, but they don't always get eliminated with cubes. So then, again, I would still have this. I didn't know that those are not supposed to be 2s. Sorry. They're 4s. Okay, this 4 down at the bottom will reduce with the 8 to give me a negative 2 here, right? So now I have 3 times negative 2, which would give me a negative 6. Ooh, it's not the same as the other value, right? It's not like the last ones. Okay, one more. I have negative 1. So what happens when I cube negative 1? I get negative 1. And then I have that times 3/4, so we get a negative 3/4. You guys got it, right? So now we're going to plot these 5 points. Okay, so let's give those a plot. It looks something like that. We have to connect them smoothly. It is obviously going to be curved, right? You can't do that with a line. This is not a line. So let me show you what it ends up looking like. That wasn't very good. Let me try it again. Maybe from the top down. That's better. I don't have a name for this. This isn't a U, it isn't a V. It's not got a name. But every cubed function looks like this. All right? Kind of looks like, I want to say a curve, but that's not really helpful, is it? They're all curves. They all look like this. All right, so one thing I want you to notice from what's been going on, we've mentioned it as we've been working our way through this. You know, how does it look like these graphs have sort of an imaging, a mirroring going on, I think was the word that Megan used. There's actually symmetry going on in these graphs. Okay, the ones that we're looking at specifically have symmetry. There's 3 types of symmetry, and we've seen 2 of them so far in this lesson. One is called x-axis symmetry, and this one looks like the graph is a reflection of itself over the x-axis, or a mirroring of itself over the x-axis. That one we didn't see. I'll draw you a picture in a minute, so leave a little space next to it for a small picture. Y-axis symmetry, we saw. The graph is a reflection of itself over the y-axis. We saw that with our absolute value x graphs. We saw that with our x squared graph. It was a reflection of itself over the y-axis. So we had things that looked like this. All right, so this graph is actually a reflection over the y-axis. Remember, y-axis is the vertical one. And so is our parabola that looked like that, right? I mean, it also has that same reflection over the y-axis. Going back up to the x-axis, we didn't have any examples of this, but, well, we actually did. We just didn't see the graph of it. But if you actually had sort of a parabola or a quadratic turned on its side, it would be an example of a reflection over the x-axis for the same reason. Origin's a little different. Origin is a rotation of itself around the origin. So you can think about being 180 degrees. That's a good way to think about it. And we did see an example of this. We saw the example when we had the cubic one. I'm just going to draw a particular, just a y equals x cubed graph, but it looks, something like this. And if you can imagine taking this top piece right here and rotating it 180 degrees, it would actually end up landing on this bottom piece. And likewise, the bottom piece would land up here on the top. That didn't draw very well. Let me try it again. Okay, so that's a rotation symmetry. We call it an origin symmetry of 180 degrees. And it's also good to notice that there's actually the possibility of having more than one type of symmetry. In particular, if you have more than one type, you'll have all 3. So here's an example of one of those. Oh, I'll draw it better than that. I know how to do it. Let's go with this. Okay, so this is, we actually have a name for this. It's called an ellipse. It looks kind of like an oval or a football or egg-shaped. And what you'll notice is that we do have x-axis symmetry, right? It's a reflection over the x-axis. We have y-axis symmetry. It is a reflection over the y-axis. And we have rotation symmetry. If I rotated 180 degrees, I would be right back to the exact same shape that I had before. So on your homework today, you're going to have a variety of questions that are going to ask you to determine, does it have x-axis, y-axis, origin, all 3, or none? And you're just going to mark down which ones of those it has, or if it has none, you're going to mark it doesn't have any.